Assalamu alaikum. That is lecture 3 for current week. Course title is Microprocessor Programming and Interfacing. Course code is CS4. We have to take quick review of the previous lecture. In previous lecture, we have covered some instructions of transfer of control group of instructions. Uh, we covered conditional jump instructions, unconditional jump instructions. Then we discussed call instructions and return instructions. In today's lecture, we have to cover the remaining instructions of instruction set. So we will be discussing loop instructions here, that is belonging to transfer of control group of instructions. Then we are going to discuss assembly language syntax. So that is the start of a new topic, that is programming the microprocessor. So we are going to study how to write a program for microprocessor. Then we have to discuss how we may use some built-in services stored in BIOS and DOS by using some instructions. Then we have to discuss how we assemble and link an assembly file to make an executable file. Then we have to so here we have to discuss loop instructions. As we have studied earlier, conditional jumps. For conditional jump instructions, we were having only one type of operand, that is short label. Same is the case here. For loop instructions, you will be having only short labels. So limit for jump is the same. Displacement may be lesser than or equal to plus 7f hex in the forward direction. In reverse direction, from the current location, you may go minus 80h locations. So that is the limit for this type of loop instructions. But loop instructions are used to repeat a piece of code repeatedly. So here you will be having negative displacements, but forward displacement are not desirable for loop instructions. So operation for loop instruction is, whenever loop instruction is occur, first of all, that loop instruction decrements the value of Cx. So Cx minus 1 will be calculated. If the value of Cx minus 1 is not equivalent to 0, uh, current value for IP will be added with the displacement and you will be having a new IP. That means loop will occur. Or otherwise, if Cx minus 1 becomes 0, so loop will be terminated and you will be having uh, next instruction written to loop instruction, or you may say that there will be no change in program flow. And as this loop instruction is having short label, so that loop instruction will be stored in 2 bytes. E2 is the opcode for loop instruction, and in the second byte you will be having displacement of 8 bit. Next loop instruction is loop E, loop if equal, or loop Z, loop if 0, and short label. Opcode for loop E or loop Z instruction is E1, and you will be having 8 bit displacement in the second byte. Here you have to check two conditions before uh, loading new value for IP. First condition is the same, that Cx minus 1 should be a non-zero value. And second condition is 0 flag should be having logic 1. So if both conditions are satisfied, then IPC will be added with the 8-bit displacement and you will be having a new value for IP. And the limit for jump is the same we have discussed earlier. So if one of these conditions are not satisfied, then loop will terminated, or you may say that there will be no change in program flow. Third type of loop instruction is loop any or loop nz. Both are same. Loop any means loop not equal. Loop nz means loop not zero. and there will be a short label. Opcode for these instructions are E0, and in second byte you will be having 8-bit displacement. So here you are having two conditions. First condition is the same, that Cx minus 1 must be not equal to 0, and second condition is 0 flag should be having logic 0. If both of these conditions are satisfied, then current value for IP will be added with 8-bit displacement, and you will be having new value for IP. Or otherwise, if one of these conditions are not satisfied, then no loop will be terminated and there will be no change in program flow. Here we are having some examples for loop instructions. First example is for simple loop instruction. So here we are having 00FF hex in BX, then we are having 4 in CX. After that we have taken input from ATH port address into AL. Then we have incremented BX, so BX will be having 100 hex after execution of this increment instruction. Then we have stored byte present within AL at offset 100x within data segment. After that we are having loop instruction. So loop will be decrementing Cx by 1. So 4 minus 1 will be calculated and you are having 3. So 3 is not 0. So loop will continue and you will be at offset 106. So at 106 offset you are having in instruction. Another byte is taken input from port address ATH into AL. Increment BX will be changing BX to 101. Now next byte taken input from port address will be stored at 101 offset address within data segment. Now again loop instruction. So Cx is having 3 minus 1 equal to 2, that is not 0, not equivalent to 0. So loop will continue and loop will take you to the offset 106. So another byte is taken input from port address ATH. BX incremented, so BX becomes 102. Now AL will be stored at 102 offset within data segment. Now again loop instruction. So calculation is to be repeated. 2 minus 1 equal to 1, that is non-zero. Again loop will continue and you will be at in instruction. Another byte taken input from port BX incremented to 103. Now AL is stored at 103 offset within data segment. Now again loop instruction, calculation is to be repeated. Cx minus 1, Cx is having 1, 1 minus 1 0, so loop will terminated. Next example is for loop NZ. In this program you are having 0 in AX, then you are having 6 in CX. Pop BX is executed to retrieve a word from top of the stack into BX. So that word is added with AX. Then there is test instruction test cx comma 4. So whatever contents of cx are ended with 4 by using this test instruction. So 6 ended with 4, you will be having a non-zero result. So 0 flag will be having logic 0. Now you are having loop nz instruction. Loop nz will be decrementing cx by 1. 6 minus 1 equal to 4, non-zero value. So loop will continue as both of the conditions required for continuation of loop nz instruction are satisfied. So loop will take you to offset 106. Now another word will be popped from top of the stack into bx register, that will be added to ax. Then again calculation is performed by using test instruction. So test will be ending cx contents that is 5 with 4. So you will be having a non-zero result. Loop nz will be decrementing cx by 1. 5 minus 1 equal to 4, non-zero value. Both conditions required for continuation of loop nz instruction are satisfied. So you will be at offset 106. Now again pop bx, another word is popped from top of the stack to BX register. That word is added to AX, then you are having test instructions. Now CX is having 4, 4 ended with 4 non-zero value, and loop and Z will be decrementing CX by 1, 4 minus 1 equal to 3, that is a non-zero value. Loop will continue again. Another word will be popped from top of the stack, then uh, that word will be added to AX. Then you are having test instruction. Now CX is having 3, that will be ended with 4, and result will be a 0 value. When loop and Z instruction will occur, that will be decrementing CX by 1, 3 minus 1 equal to 2, that is non-zero. But second condition required for continuation of loop and Z instruction is not satisfied now, as 0 flag is 1 now, so loop will be terminating. In third example, we are having loop Z instruction. We have moved FFFF in AX, we have loaded CX with 6, then we have executed increment AX, so AX will become 0 0 0 0, and test will be ending contents of AX register with CX register. So 0 will be ended with 6, and you will be having a 0 result. So 0 flag will be having logic 1. Loop Z instruction will be decrementing CX by 1. CX is having 6, 6 minus 1, 5, non-zero value. So both conditions are satisfied for loop Z. So loop will continue and you will be at offset 106. Now again AX will be incremented. So AX will be having 1. And test instruction will be ending 1 with 5, and you will be having a non-zero result. And loop Z will be decrementing CX by 1, 5 minus 1 equal to 4, that is non-zero, but second condition required for continuation of loop Z instruction is not satisfied now, as 0 flag is having 0. So loop will be terminated. So we have covered almost all the instructions present within the instruction set of 8088, 8086 microprocessors. Now we are going to start a new topic, that is assembly language programming. In this section of our course, we have to study how to write an assembly language program, and that program should be recognizable by the assembler, Microsoft Microassembler, MASM. And MASM will be generating object file when you will be passing that assembly file through MASM. And in the second step, that object file will be used as input to the linker, and linker will be providing you the executable file, and your computer may be able to execute that executable file for having the operation for which you have written the assembly language program. So the assembly file may be in lowercase or uppercase, but standard practice is to write the code in uppercase, and rest of the text present within the assembly file will be in lowercase. So in assembly file you will be having assembly language statements, and there are two types of statements. First one is called assembly instructions, and instructions are converted into machine code by assembler, while second type is assembler directives. Assembler directives instructs the assembler to perform from a specific task, like you may assign a byte or word in memory, or you may define uh, an string in memory, or you may assign a label to a constant number, or you will be declaring the start of a procedure, or you will be declaring the end of a procedure by using these directives. So many directives are available, and each directive is having some meaning for assembler. So whether your statement is an instruction or directive, there will be four fields. Uh, First field is name field, then operation, then operands, then you will be writing some comments. To separate these fields, at least one blank space should be present, or you may have a tab between these fields to separate them. Here we are having some examples for assembly instructions. So first, in the first line you are having move ax comma bx. So move is the operation, ax and bx are the operands, and here colon is the name for this instruction. After semicolon whatever you write, that is treated as comments. So you have defined the operation of this instruction in symbolic notation, said that bx contents are to be copied into ax contents. Or you may write the operation in wording that bx contents are moving into ax contents. Then in the second line you are having jmp here. So here is used to point to move instruction here. So here is the operand for jump instruction, but actually here is the address for move instruction. So jump unconditionally to here, that is the comment after semicolon for this jump instruction. Then you are having XLAT instruction, translate instruction with the no operand, and then you are having NOP instruction, no operation instruction, and no operation instruction is also having no operand, zero operand. In the last you are having an IML instruction. IML instruction of three operands are available in 32-bit processors. So we have taken this example to show that there may be three operands possible, but this instruction is present in processors 80286 onward until Pentium 4. So that instruction will be multiplying WD1 with 20x and the result will be stored in AX. Now we are having some examples for assembly directives. So first statement is BT1 DB 2E hex, and after semicolon you have written the operation of this statement. So BT1 is the variable name, DB is the operation that define byte, and at BT1 offset within data segment a byte 2E is to be stored. So after execution of this statement in data segment at offset BT1, you will be having data 2E hex. So that is written in the comment after semicolon. Second statement is ARR1 DB 10 hex. DUP means duplicate within small brackets question mark. So you have defined an array having 10 h bytes. Initial value is not defined, so all the initial values will be 0 in memory. So you have defined an array of 10 elements, each or 10 bytes, each having value 00. Then you are having MSG1 DB. In single quote or double quote, you may write some message, or you may write some number or special character. ASCII of that, whatever matter you have written within a single quote or double quote, that will be stored in memory in the form of ASCIIs. So you are having, this is microprocessor programming and interfacing course content, and in the, before closing the comma, inverted commas, you have written dollar sign. So dollar sign will be terminating this message when you will be printing that message on monitor screen. So all the letters or blank spaces or numbers or special characters written within single quote ASCIIs of those characters will be stored in memory. Now next statement is WD1 DW4D50 hex. So you have stored a word by using DW directive, and address for that word will be equated with WD1. So in the comment you are having that at offset bit WD1 within data segment you have stored a word 4D50X. Now another statement data1 DB 100, 760, 11111010 B binary, 5V hex. So you have stored 4 bytes in memory by using DB directive. So 100 equivalent of 100 decimal is 64 hex. So first byte is 64, then second byte is 76 O, equivalent of 76 octal is 3E within hexadecimal, and then you are having a binary number equivalent of that, if equivalent hex value for that binary is F6 hex, then in the last you are having a hex number 5vx. So 4 bytes are to be stored starting at data 1 offset within data segment. After that you are having equate EQU statement num1 EQU 10,000. Equivalent for 10,000 is 2710 hex. That value is equated with the symbol num1. So whenever you are going to write num1 in any program, that numerical value 2710 will be replaced there by the assembler. And by using EQU instruction, you may equate 16-bit number to a label or name. Then you are having an statement main proc, that is the start of main routine. That statement is declaring that now onward you are having code for main procedure. And in the end of the procedure you will be writing main and p, that is the declaration that main procedure is completed, and that is the end of main procedure. So here we are having some details for name field. So name field may be used for instruction labels, procedure names, and variable names. And assembler will be translating names into the memory addresses. And name field may be of 1 to 31 characters long, and it may have letters, digits, special characters, and these special characters are allowed: question mark, dot, at the rate sign, underscore, dollar sign, and percentage marks. You may not use static sign or a cap or hash sign within the name field, and spaces are not allowed within the name field. Name field may not start with a digit, but you may use a digit within the name field or in the end of the name field. And uppercase and lowercase names are the same. If you define a name in uppercase and you use that name field in any instruction or anywhere else, you may use lowercase for that. The operation field is the in case of instruction, that is the mnemonic of instruction, or you may say that the symbolic opcode in case of assembly instruction. And assembler will be translating this mnemonic of instruction or symbolic opcode into equivalent machine code, hex numbers. And some of the examples are mov, move, add, add, sub, sub. These are the mnemonics for different instructions. In case of assembler directives, operation field will be having sudo operation code. That means uh, this sudo op will not be converted into machine code, but it will be telling assembler to do something. For example, proc directive is used to declare the start of a procedure, and you may have db directive in your program. So db directive will be telling that you are going to define a byte by using db directive. Db means define byte. In operation field, for an instruction, you will be specifying the operands on which uh, you have to take some action. That may be a data transfer operation, or data manipulation operation, or transfer of control operation. Uh, some instructions will be having 0 operand, some will be having 1 operand, and some are having 2 operands for 16-bit microprocessor. In 32-bit microprocessors, 3 operand instructions are also allowed. In case of assembly directives, that field will be having some information regarding the operation, or you may say that that will be having an additional information regarding the operation field. Now we are having comment field. Comment field is an optional field. You may write a comment for assembly instruction as well as assembly directive. Uh, the comment field will be starting after semicolon. Whatever you will be writing after semicolon, that would be treated as a comment, and assembler will not be reading whatever is written after semicolon. So in case of assembly language program, to understand an assembly language program is not easy for a beginner or a new user. So by adding comment into your program, that will make uh, easier for the reader to understand your program. Till now we have discussed different fields of assembly language statement. Now we have to discuss the service routines which are required to write our assembly language file. So during our assembly language file, we will be calling some service routines, pre-stored service routines. So one category is the BIOS service routines, and second category is the DOS service routines. BIOS service routines will be stored in ROM, and that service routines will be interacting directly with the IO ports present in computer. And some of the examples are moving the cursor or scrolling the screen. Second type of routines are DOS service routines. These service routines will be performing more complex tasks for us. Some of the examples are taking single character input from keyboard, or outputting single character to screen, monitor screen, or displaying a string on the monitor screen. These are the examples for DOS service routines. So int instruction will be used to call DOS or BIOS function within our assembly language file. Format for int instruction is int and interrupt vector number. That vector number may be greater than or equal to 21 hex and lesser or equal to FFH. Or you may say that that will be an 8-bit number ranging between 21 hex and FFH. So here we are talking about interrupt 21 hex. That instruction may invoke a DOS function depending upon the depending upon the contents of AH register. Now here we are having some examples for calling some frequently called functions of DOS by using interrupt 21H. So if you are having one in AH register and you execute interrupt 21H instruction, so that arrangement will enable you to take single key input from keyboard, and whatever key user presses in response of interrupt 21H instruction, that key will be displayed on monitor screen. So that is called single key input with echo. And ASCII of that key which is pressed by user will be moving into AL register. Or you may take input by placing 8 in AH. You are having 8 in H and you have executed interrupt 21H. So ASCII of key pressed from keyboard will be in AL after execution of interrupt 21H, but that key will not be displayed on monitor screen. So that is called single key input without echo. Now next example is to output single character on monitor screen. For that you will be having 2 in AH register. So you have moved 2 in AH and you are having ASCII of capital A in DL, that is 41 hex. After that you are having interrupt 21H instruction. So when interrupt 21H instruction will be executed, capital A will be displayed on monitor screen. Then you may invoke string display function by having 9 in AH. So here you are having 9 in AH register, then you have written an statement, an instruction of LEA, that is load effective address. Within DX you are having address of MSG1. MSG1 we have discussed earlier in slide 6 of this lecture. So you are having a message in memory and you have loaded the starting address of that string message within DX register by using LEA instruction. So after that you are having interrupt 21H instruction. So when interrupt 21H instruction will be executed, a string will be displayed on monitor screen. Next function is to input a string from keyboard. For that AH should be having 0AH, and after that you have to move the starting address for string in memory within DX register. So we have moved FE in DX register. So when interrupt 21H will be executed, you will be able to type some message or a number or special character from keyboard. Uh, but microprocessor will be storing that inputted characters within memory at offset dx plus 2 within data segment. So that is the implicit operation. Last function for interrupt 21x is to exit DOS from your program. So for that you will be having 4ch in AH register and you will be executing interrupt 21h instruction to exit to DOS. Now we are going to discuss the steps involved in making the exe file from ASM file. So first of all you have to create an ASM file. Here we are having name for ASM file first.asm. So for creating first.asm you may use any editor like Notepad, WordPad or Word or DOS editor, whichever editor you may use. You will be using that editor for writing your assembly file. Then you will be saving that file within the folder where you are having the assembler file and linker file, as you have to pass this ASM file through assembler. Here we are having masum.exe file within a folder named masum within D drive, and we are having linker file, that is link.exe within the same folder, that is masum folder within D drive D colon. So if you are having you are going to assemble your file and you are in the C drive, then you have to change drive first by typing D colon enter, and after that you have to go into the folder masum. For that you will be typing cd masum. So your prompt will be like that: d colon backslash masum and greater than sign. Now you may type the command line for converting uh, purse.asm file into obj file. So for that the command line is masum space the file of asm file name of the asm file. First, writing .asm is optional. You may write or you may skip that extension of the file. So when you will be pressing enter, Masum will be giving you the message with the obj file name first.obj. If you want to accept that name, you have to press enter without writing anything. Then Masum will be giving you the file for cross-reference file. If you want to create cross-reference file, you have to write the name first and press enter. In the next line, you will be having a message for listing file creation. If you want to create listing file, then you have to write name first and press enter. In response, if you are having no message, that means your ASM file is converted into the OBJ file, and CRF and listing file are also be made by the MESM if you have opted for these files. Now second step is to link the OBJ file with the exe file. For that the command line is link space first, and you will be pressing enter. Here the input file is the obj file. If you write link first dot obj, that is okay, or otherwise with the writing the file name without the extension, that is also okay. So you write link first and enter, press enter. You that will be creating exe file for you. So you will be having a message for exe file name first.exe. If you want to change the name, you have to write the name. If you want to accept the name first.exe, you have to press enter without writing anything. Then you have to you will be having in the next line message for map file. If you want to create the map file, then you have to write the name of the map file first, and you will be pressing enter. So first.map will also be made by linker file. So after these two steps, you will be having 6 files. Name first.asm you have written by using editor. In the first step of assembling file, you will be having 3 more files: first.obj, first.crf, first.lst. In the second step of linking, you will be having 2 more files: first.exe and first.map. So these are the steps. By using editor, you have made .asm file. Then you have provided this ASM file to assembler. Assembler will be making .obj file for you. In the next step, you will be providing this obj file to linker, and linker will be generating the exe file for you. So that is the end of the current lecture.